All right, so today I'm going to be discussing about modes. So the first, I suppose, place to start here that is appropriate is simply to define what a mode is. So what is a mode? Well, there are various ways of thinking about it. There are a variety of definitions. But quite generally, if we have a system that is oscillating, and one example of a system that is oscillating is if you attach a string in between two walls. You can have an oscillating string that's attached to two walls where you have, a 0 here at the node. This is just one of the so-called modes of this system. A mode is simply defined as anything that is oscillating, any system that is oscillating, oftentimes a bound system. Everything that is oscillating is doing so at the exact same frequency. So you can imagine here that you have this string here, and you have a point here that is oscillating, and I'm going to just put this in this color. So you have a point here that is oscillating, you have a point here that is oscillating, this is oscillating. So you can just imagine this string coming down and up and up and down and up and down and up, and everything that is oscillating, whether it's the point very close to the center node or if it's this peak over here, is doing so at the exact same frequency. That is, the period, the time it takes for each point to go up and back down to where it started is the exact same. And so this is one instance of a mode. Another instance of a mode is if you take a look at your coffee cup, and let's say you have or not even a coffee cup, a cup of water, doesn't really matter what it is, any sort of cup with fluid, and you have it on a table. You have it on a table and you're playing some sort of music in the background, and the table starts vibrating, and you can clearly see some patterns forming at the very surface of the liquid. And this pattern, I'm not going to attempt to draw that pattern, but like it has a very weirdly shaped pattern, and if you've seen this before, you know exactly what I'm talking about. Well, this right here is more of a two-dimensional type of mode. That rippling pattern that you see, that is oddly symmetric, that appears to be symmetric radially at least. That is another instance of a mode of this particular system, that is the cup filled with water. And in that instance, once again, you were having oscillations at the exact same frequency throughout the entire surface. And so you can look these up online. There's plenty of instances of what a mode is. And you have modes in electromagnetic waves, you have modes in atoms, you have modes in acoustic waves, you have all sorts of different modes. And so in mechanical oscillations, in the case of a mechanical oscillation, you have what are known as normal modes. This is what we typically call them. So in the case of this string right here, you can call that a normal mode. So normal modes is a very common term used. In mathematics, for those of you who are math savvy, in which case a lot of this review should be very simple to you, mathematical definition or mathematical name of a mode is often regarded as an eigenfunction. An eigenfunction. And so in linear algebra, you deal with such quote-unquote modes. And so if you write down an eigenequation for these normal modes, really the modes are the eigenfunctions. They're also known as basis functions. So these are all well-known terms. You also have in quantum mechanics. In quantum mechanics, very, very similar to the mathematical description of it, we call them eigenstates. You have eigenstates. You also have basis states. You also have orbitals in the case of atoms. You have atoms that often refer to these so-called eigenfunctions as orbitals. And so you have multiple instances of this concept of a mode whereby everything that is oscillating, at this exact same frequency. And so there are multiple instances of this. So you can go and look at it yourself, look it up yourself if you're kind of, not entirely familiar with the concept of a mode. But we're going to get into this concept throughout the entire module, really, because modes are quite central to quantum mechanics. It's kind of forms the essence of the time-independent form of the Schrödinger equation. It's simply an eigenequation for which we solve the eigenfunctions for, or the eigenstates for. So we can start off with the more explicit example, actually. In the example of and this is often invoked whenever talking about modes and oscillations in any course, that is the simple harmonic oscillator. Simple harmonic oscillator. And the simple harmonic oscillator, we can really see one if we attach a mass on a spring. Any mass of mass m on a spring, if I take this system and I apply a force, let's say for example the original position here was 0, and I applied some force and displaced the mass a distance z, right? So I took my hand and I pushed it down a distance z. Obviously there's going to be some sort of restoring force in this direction, and just for us to note, to be clear, I'm defining the positive direction as down. And so if I apply a force downward, the force, the equal and opposite force that is pushing against my hand, is obviously due to the tension on the string, and that force is in the opposite direction. And so we can call that restoring force. It's called the restoring force. We can call that F is equal to minus K times Z. And so this is the well-known restoring, the force equation for the case of the mass of the spring, where this term here is known as the spring constant. Spring constant, and the unit of this, of course, is in, you have newtons per meter times meter. That of course gives us newtons. And so this is the restoring force. Of course, any sort of force using Newton's second law, indeed, there is a particular acceleration associated with it. If I have a non-zero force, and I'm applying it in any given direction, I am accelerating the mass of, I'm obviously accelerating the mass per Newton's second law. Per Newton's second law. And so that is F equals ma, of course, and we're very familiar with this. And this is equal to m times dv dt, which is of course equal to m times d2, or the second derivative of the position. And so this is F as well. And so of course we can relate the two. So let's see what happens when we actually equate the two. We have F is equal to minus kz, and F equals m times the second derivative of the position. So we have minus kz is equal to d squared z over dt squared. And we can, sorry about that, there's an m here, and we can divide the m over. Minus k over m times z is equal to d2 z over dt squared. And for many of you who aren't familiar with this, it actually turns out that this term here, this k over m, is a well-known term. It actually gives us a value that is equal to the square of the oscillation frequency. right? And the angular frequency, actually. So the angular frequency, right, which is simply 2 pi divided by, or I shouldn't write that in red, but the angular frequency of this system, you know, as it's oscillating up and down, is simply 2 pi over the period, right? So the time it takes for this mass to come back, to go up and back down to its original position, is simply equal to t, and so the angular frequency is 2 pi over t, which is also 2 pi over f, which is of course simply equal to, and we give this a variable called omega. So omega is the angular frequency, and it turns out that k over m gives us this omega squared. That is, omega squared is equal to k over m. So it actually turns out that when you evaluate this term, it gives us this omega squared term. And so we can rewrite this equation up here as minus omega squared z equals d squared z over dt squared. And so this form of the equation right here, in case many of you haven't noticed, or perhaps some of you haven't gone through this, is an eigenequation. Eigenequation. It's a very well-known term, very well-known form, a mathematical form, and we're going to come back to this. Essentially, the idea is that you have an operator. In this case, we have this operator called the second derivative, operating on z, the function z, and we are getting an eigenvalue that is this minus omega squared term times that same function, right? And so the form of these so-called eigenequations are a, the operator, a, this is kind of like some operation. In this case, it's a second derivative. It could be the first derivative. It can be a big matrix. It can be all sorts of different things. It's essentially something that turns the function z into you know, some other function. That's generally the definition of an operator. And so if it is an eigenequation, if what we have here is an eigenequation, whenever you apply this operator to a corresponding eigenfunction, which is this z, you're going to get back its eigenvalue times that exact same eigenfunction, right? And so here we have the eigenvalue. Actually, I'm going to the common variable for the eigenvalue is lambda times z, and so here we have minus omega squared, and here we have this d2 over dt squared. So this is an eigenequation. So something to note there. It's important. And so what is a solution to this eigenequation? Of course, this is simply a second-order differential equation, and these differential equations have solutions to it. Well, I can immediately spot one particular solution. And note that this is a particular solution. And one particular solution to this is z equals sine of omega t. And we can tell that this is a particular solution because if I take the double derivative of this, of course I'm going to get of sine of omega t. Of course I'm going to get dt, so the first derivative of omega cosine of omega t, which is equal to, taking the product rule, omega d dt of cosine omega t, which gives us back minus omega squared sine of omega t, right? And so this here is equal to minus omega squared times z. So we're back to where we started, of course, right? So this is d2 dt squared times z is equal to minus omega squared times z. So far so good. I can write a particular or a general solution to this equation I'm not going to go through the entire derivation, of course. This isn't a differential equations course, but I'm going to give you the most general solution that allows for virtually any amplitude or phase of the general solution. And that is going to be, so this is the general solution. Of course, this is for a one-dimensional case. A sine of omega t plus b cosine of omega t. So since the cosine is 90 degrees out of phase of the sine, and you have a and b, which are any arbitrary coefficients here, we can essentially say that this general solution applies for really any one-dimensional harmonic oscillator. So we have this single harmonic oscillator that's described entirely by this solution here. So we clearly, this particular solution, we can arrive at it by setting b equal to 0 and a equal to 1. And so you have this as a general solution. And so one thing to note here is that in the case of the simple harmonic oscillator, although we can have different amplitudes, we can have different amplitudes for the different phases, right? And we have these different phases here that are 90 degrees out of phase with one another. You always have the exact same frequency, which is omega. So everything is oscillating at this exact same frequency, omega. And so this is one thing that is important to keep in mind. And we have to recall here that this term omega is obviously just a factor of 2 pi away from the actual frequency. Okay, so this is really just the one thing to recall here. And this kind of concludes this part of the lecture. We're going to do a problem on this, and we're also going to move forward and work with classical the classical wave equation, as well as the standing waves and the Helmholtz equation. And so I'll see you guys in the next lecture.